All right, so just try and expect. Now remember, you expect a quiz anytime, any day. Always be ready. But I want to get at least one quiz in a week, and that way, if we have enough, we can drop a few of them. If I only have 5 quizzes, then I've got to keep all of them. So the more, the better, and it also gives you an opportunity to get an idea of the things I'm asking, and forces you to kind of keep up with things. Right? So let's talk about the quiz. What'd y'all think? Was it fair? Within the realm of being fair? You don't want to answer. All right, so I ask about left and right continuity and just overall continuity at 4 points. So at the point x is -3, right here, we are what? Left continuous. Are we right continuous? No. So if you're not left continuous, if you have to have both left and right continuity to be continuous. So the only way you're ever going to be continuous is if both the left and the right are going to the same place. So left yes, right no, continuity no. At, what was the next point? 0? At 0, left continuity? This is going to -infinity. I kind of put little dots there to kind of show you. But it would need to go to a certain point to be left continuous. So no. How about right continuity? Yes. Continuity? No. How about at 2? Left continuity? No. You have to have a dot, right? Right continuity? No. Continuity? No. How about at 4? Yes, yes, yes. Now I didn't put the dot, but it's implied. If I don't put a hole there, then it's implied that it's a dot. So yes, yes, yes at 4. Understand? All right, now the last part, limit as x goes to what? Infinity of 1 over x cubed. This comes from the notes, the lecture course video for today, which you were supposed to watch before you came here today. And there was, again in the notes, a point where I said very important, where is it? There it is. Limits at infinity, an important property that if you have the limit as x goes to infinity of 1 over x to the n power for any value of n where n is 1, 2, 3, 4, doesn't matter what this integer is as long as it's positive, that limit is always 0. Yeah, I mean, it does approach 0, but we put equality for limits. All right, so again, the theme here being you had a question that had to do with what we did last time that your homework dealt with, and we have a question that has to do with something that you were supposed to look at before you came in today. Maintaining that theme, we'll just continue to maintain that theme, all right? Do you think that's a fair question? Okay, all right. I hope so. Not trying to make this impossible, but I do have an expectation here that you are going to prepare for each day. All right, any questions over homework? Out of 1-5, continuity. Which one? 11? Did I do 11 or no? I did not do 11? Of course not, right? Okay, so let's take a look. I'm recording and my mic is on. Good, all right. Suppose f and g are continuous functions such that g of 2 is 6. Limit as x approaches 2 of 3 times f of x plus f of x times g of x equals 36. Find f of 2. All right. So y'all don't get offended by this, okay? Please don't get offended. I've had classes before where like students have been, they've actually had issues with hygiene, where they just like, I don't know if you've ever been in a class where like someone like really smells bad. Okay, someone smells really good today, but it's really good. Like it's, whatever you put on, there's a lot of it. I don't know if I'm the only one here. Maybe I'm just sensitive, but no, am I the only one? I'm the only one.
Smell like a guy or a girl?
I don't know what it's just really intense, no? Okay, I think maybe it's just me then. I'll just shut up. Ignore me then. My wife always tells me, she's like, you know, I don't know. She puts on perfume and I'm just like, God, you know, like it smells good, but not at that strength. So, okay. All right, if I'm the only one who smells it, then, all right, never mind. Okay, so what were you thinking about this one? You asked, right?
I thought if you just plug in 6, I mean, it's not for f of x, but I got the wrong answer.
Okay. There's got to be some other information stated here. Suppose f and g are continuous, right? F and g are continuous functions. That means that everywhere on f and g, you pick any point, you come in from the left and the right, you're headed towards the same place and to a point. So let me just draw a picture. Whoa, this one's done. All right, where's that trash can? Okay, watch out. I mean, everybody watch out. I'm not that good at this. Oh, it's going to be a good year. Spurs going to have a good year. No. Okay, so what? First thing, g of 2 is 6. So if I go out to 2, I go up to 6. I know this is a point, and g lives there, right? That's g. I'm just going to put a little g above it so we all know. And what I also know is that if I take the limit as x approaches 2 of 3 times f plus f times g, that should be equal to 36. All right. I'm supposed to find f of 2. So somewhere around here, right? Somewhere around here at 2, f lives somewhere. How do you know that f is defined? It's continuous. So it lives somewhere, right? I don't know where. This is f, I'll even put of 2. And this is what we want to know. This right here I'll even put is g of 2 is 6. That's that point. What I'm given is that if I take, let's say, limit as x goes to 2 of just this piece. And remember, with limits, you can split them, right? You can split these. If I take the limit, why can I split that? The limit laws, right? I could write 3f of x, and I can also take the 3 out because the limit laws tell me that constants can come out. So this rewritten using limit laws is that. Plus, now when you have a product in a limit, can you split it into 2 limits with the product? Yes. So I can write plus limit as x approaches 2 of f of x times limit as x approaches 2 of g of x must be 36. Do you follow what I've done? Just kind of split this all up using limit laws. Do you know any of those pieces?
G of x.
You know that this limit right here must be what? 6, because it's continuous. Whatever happens at 2, I know that g must go in there, right? So it's got to go into the same place. So the limit from both sides must also be 6. So I know this is 6, right? And let me erase this. Is there anything you can tell me about this piece and this piece, other than they're the same? What do those two have to be equal to?
Each other.
Each other, yes.
And g of x.
Not g. Is it? Do these have to be equal to g of 2?
They equal to 2.
They have to be equal to. I'm hearing so many different things.
They have to equal 2 down g of 2.
Not g of 2. Is f continuous?
No, because g is, right?
G is, they're both continuous. It's given, yes. That has to be given, though. So if f is continuous, what does it mean for a function to be continuous at a point? It means the limit as x approaches a of f of x equals what? F of a? So since f is continuous, the limit as x approaches 2 of f of x should be equal to f of 2. So I can replace this limit with f of 2. Can't I? Because it's continuous. I can replace this limit with f of 2. And hey, that's a good thing because that's what I'm trying to find. So this equation now looks like this. 3 times f of 2 plus f of 2 times 6 equals 36. Any ideas on what to do here? Trying to solve for f of 2, right? Say again?
Divide both sides by 6.
You could divide both sides by 6. You have a 3 over here also. How about these? Are these together? Are these like terms now?
Yep.
They are like terms, aren't they? So that's really nine of those things, right? 9. 3 of these plus 6 of those is 9 of these. And then you divide by 9 on both sides, and f of 2 then must be 4. Yes?
Would it be wrong to factor out the limit?
You could have factored out the limit, yes.
It's just a
Yep,
variable.
it's just algebra, really. Yeah. You could have looked at this as like a variable and just said factor it out. But at some point, you would have needed to just make the connection that that is f of 2. And that's the continuity that gives you that. Yes?
When I realized those two were variables, I just put 9 times the limit of x as it approaches 2. Or I mean, just 9 limit of x
Yes.
as it approaches 2
Uh-huh.
of f of x equals 36.
Yes.
Okay.
And then you could have divided both sides by 9, and you would have had the limit as x approaches 2 of f of x must be 4, right? And from that, you need to be able to say, well, look, if it's continuous, wherever the function heads is also what it's defined to be at 2. So that's why f of 2 would also have to be 4. Does that match up with the book's answer?
Yes.
Yes? Okay.
I got like a kind of a weird question.
Yes.
Like, I understand that you're assuming that they're both continuous.
Yes. Not assuming it's given.
Right.
Yeah.
So it's given that they're both continuous.
Yes.
So if they're both continuous and it's both approaching 2, like, how would that be possible? Like, if you do a vertical line test, you have 2, they're different.
They're different functions. Each function by themselves is a function, right? Each curve by itself is a function. F and G are 2 different functions.
Yeah, okay, I get it.
Yeah, we have 2 different curves.
Okay, that makes sense. Okay, so that's the...
You got it? Okay, good question. All right, I guess we'll start with today's stuff then. So today we are going to talk about a new concept, all right? But I handed you a sheet of paper. Everyone should have a copy of this on the desk. If you don't, let me know. Do you need one? Oh, here's some extras. It's like a table, and it has these different things here. I want you at the top of this to write limit summary. I forgot to put that there when I made it. Limit summary, just put that at the top. Everyone has one? Yes? Okay, you are not allowed to use this on a test, but it is something that you can help, use to help yourself prepare for a test, and that it gives you somewhere to focus, all right? So, what you need to understand is that every single thing you see here is what you're getting as the result of taking a limit. So in the top left, I have all these things written. 0 over 0, infinity over infinity. 0 times infinity, infinity minus infinity. 1 to the infinity, 0 to the 0, and infinity to the 0. That's everything in the top left corner, right?
What happens when you multiply 0 times infinity?
Yeah, what happens, exactly. So what I just said is, remember that every single one of these is what's happening when you are taking a limit. Okay, when you are taking a limit, you're getting 0 over 0. You're taking a limit, you're getting something that's becoming infinite over something that's becoming infinite. Now this is going to answer your question. You're taking a limit and you're getting something that is approaching 0 times something that is approaching infinity. Okay, so I'm not saying here that 0 times infinity is anything. I'm saying when you look at a limit and one of the things is getting really small while the other thing is getting really big, what happens? It's kind of like when we say the top is getting small, bottom's getting small, 0 over 0. We've seen we get answers, don't we? That's how I started this whole class out. What happens when we have 0 over 0? So anytime we see any of these, we're going to have to do something to figure them out. The only thing that we've looked at up to this point in this class is this. All right? That's all we've looked at. Today, we will cover this scenario, and everything else is going to come much later. And the reason is because to do some of these, we can't put the carriage in front of the horses, right? You got to get the horses in front of the carriage. Believe it or not, if we try and do these now, we're just going to be stuck. So we need to add some tools to our toolbox before we can even attack these. All right? We might be able to address that one, but the rest, we're just kind of wave our hands at it. All right? For now. All right? So the key, though, is that if you look at a limit and you see any of these happening, you're going to need some algebra or a trick. Right? That's what you're going to need. Now, before I look at the rest of that table, let's just discuss again why this is such a problem. 0 over 0 is a problem because we get like this division by 0 mixed in with this like concept of almost, this is like supposed to be almost a 1, right? Anything over itself. So we knew that was a problem already. Infinity over infinity is a problem because if your numerator is getting really big and your denominator is getting really big, it's kind of like you need to know a little more. Like how fast is this one growing compared to how fast this one's growing? And that comparison is what's going to give us an answer. So these are open questions in our mind. Like we don't know what happens. This one of them gets small, the other one gets big. Who wins, right? Who wins? Do you see the problem, the conundrum here? It's like a tug of war. Who wins this battle? This one also. Get a huge number. Subtract something that's getting, not a huge number. You get a function that's getting really big. You subtract a function that's getting really big. Who wins that? Right? What if this was a plus? Would it be a problem? No. Big plus big, big, right? But big minus big, that does not equal 0. That's, who knows? It depends. Yes?
I was just curious, why is 0 times infinity an issue? Because 0 times anything is 0.
Wonderful question. Who can answer that question?
Is it because infinity can just keep going or something like that?
No?
Because the equations where you get 0 times infinity, it never actually hits 0, it just approaches 0.
That's the key.
Really close.
What I'm saying here, and this is why I said it in the beginning, so make sure you understand. I'm saying when I take the limit of something, it's going to 0. Let me just write an example of one of these right here, okay? Limit as x goes to, well, I haven't used infinity in this class yet, so how about this? X minus 5 times, okay, I'm having to make this up on the fly. E to the 1 over x minus 5. All right, there we go. And I have to approach from the right, sorry. All right, so I'm just making this up. As x goes to 5, this goes to what? It's going to 0. Is it 0? No, not if I'm approaching, right? I'm approaching. So this is getting closer and closer to 0 times. Now, this right here we have to deal with today. We are not ready for this. But you have to believe me when I say that this goes to infinity. And e to the infinity, remember what the e function looks like? It goes like this. That goes to infinity. So we have something this is getting huge, this is getting small. Who wins? I'm not saying that this is the number 0 times infinity. I'm saying you have an expression that is approaching 0 times an expression that is approaching infinity. You sure you're okay with that?
Yeah.
Is everybody okay with that?
I just want to make sure that I had the difference.
Yes, good. Because I've even had students come back to me, like I remember I had this one student, it was probably about 8-10 years ago, who like called me up like 3 years after I had them in my class and was like, you told me that 1 to the infinity and all this stuff, and they didn't understand it when I presented it. I'm not telling you that 1 to any power is anything other than 1. Okay, if you take 1 and raise it, give me a power. I don't care what the power is. Give me a number, whatever. That's 1. Okay? But if you have something that is approaching 1, raised to a power that is approaching infinity, that is a problem. Approaching 1. So what's a number that's close to 1? How about 1.0000001? Now raise that to the, 10 billion. That's going to get bigger because it's bigger than 1, right? It's going to get bigger because this makes it want to get bigger, right? But if it was 1, this wouldn't matter anymore, right? So you've got this battle again, this tug of war. Look, we're going to address all these later. I'm just trying to get you to see that they are problems. 0 to the 0, why would that be a problem? Something getting really small, raised to the 0. Anything to the 0 is usually 1, right? But something that wants to get small should be allowed to get small and just go to 0. So the base is like, hey, I want to be 0, let me be 0. And the exponent's like, no, because anything that's raised to 0, you're going to be a 1. They're like not happy with each other. That makes sense? This one, same thing. Base is like, I want to be big. I want to be real big. And the same stubborn 0 is like, no, no, no. Anything raised to me is 1. And so they're like, And believe it or not, E, that number E that we studied many, many years ago in college algebra, this is about 2.718 something. The definition of E, if you want to define it, if you want to tell someone, hey, you want to know what E is? It is actually this limit. The limit as x approaches infinity of 1 plus 1 over x, not 1 over x. That's not 1 over x. 1 over x raised to the x. That is the definition of E. That's it right there.
I actually have that written in my notes.
You do?
And from algebra.
Huh. Yeah, I probably talked about it. So look what's happening here. Imagine that x gets big. What's 1 over a huge number?
Really small.
Really small, but it's something, right? 1 plus a really small number is really close to 1, isn't it? Raised to something that is becoming infinite. Something like this happens, and there's the tug of war. Who wins? In that particular case, and only in that case, they compromise. They say, okay, look, you're stubborn, I'm stubborn. We're just going to agree that we're going to approach a value. And the value that this particular limit approaches, it converges to that number. That is the definition of E, 2.718. So I challenge you on your own time to just get a value of x right now, not right now, at home. Plug in a value of x here, 10. And I bet you it's close to 2.718. If you take a bigger value, plug in 10,000, it'll be even closer to 2.718. Plug in 1 billion, it'll be even closer. And the further out you go, the more correct digits of E you will have. And if you could go to infinity, which you can't, if you could, that would be E. That's what E is. Okay. We're getting ahead of ourselves. All of these present problems. Does this present a problem? If we ever see a limit do that? No. I want to be big, right? This guy's like, I'm going to help you. Right? I'm going to help you get there. And that's not a problem. So people think like any combination of these things, they're like, yeah, it's always bad, it's always bad. No, you have to know which are bad and which aren't bad. Can someone give me another example of one that would not be bad? Say again? Negative infinity to the negative infinity. Yeah, that wouldn't be bad. What would that go to though? What's that? 0. What? Okay, anything raised to a negative number is the same as 1 over that raised to a positive, right?
Oh, right.
Right? If I have like x to the negative 2, that's the same as 1 over x squared. So if I have something raised to negative, I can look at it as 1 over that, raised to the positive. Now, what does negative infinity to a negative power do? That should be a really big number, shouldn't it? Yeah?
But it depends on what
It depends on the power, because if it's even, and there's decimals in there too. This is actually a bigger problem than we even want to address. It is. It is. Well, I mean, you said, right, you want to know what this did. This is actually pretty bad. It's pretty bad. And you might remember from when you studied exponential functions in college algebra. Do you remember this is the general version of an exponential function? something like that, a to the x. And we had a very strong condition that a had to be positive, that our bases had to be positive. And the reason why is because if you start taking negative bases and started raising them to powers, your graph just starts doing crazy shit. Because we know that negative numbers raised to positive even integers is positive, but raised to odd integers is negative. So your graph starts to scatter around like salt and pepper up and down. It's a mess. So we just throw them out. All right, I need to get this train back on the tracks. Just please understand, all of those we will deal with, but they all inherently have problems that are similar to the problems we have here. We just don't know what they are. We can't determine what the limits are just by looking. Just by looking, we can't determine it. And these are called indeterminate forms. That's what we call them. So we will focus on the one I circled in red. And then look at the rest of that sheet. The top right corner says 0 over fixed equals 0. This means that if you take a limit ever, and your numerator is not 0, is approaching 0, and your denominator is approaching a fixed number. And at the bottom of the page, I tell you what I mean by fixed. What do I say? That's not 0 and or bounded. And I'll tell you what I mean by and or bounded later. So it's like you take a limit. I'll give you an example of this. X goes to 4 of x minus 4 over x. Look at this limit. What's the top going to? 0. So it's approaching 0 over 4. Answer 0. Done. There's nothing to do. It's okay to have 0 happening on top and something other than 0 happening on the bottom. That's fine. This is not calculus. This is just a simple, analyze, boom, we're done. This is going to happen very seldom. But if we ever see it, we're done. Now, what about, let's do the bottom right one. What if you flip it, you put the fixed on top? If you ever see this happen, I even put here plus or minus. So it doesn't even matter if the top is positive or negative. If it's headed to a fixed number on top and the bottom is headed to infinity, and please add to it positive or negative infinity, it does not matter which one it is. The answer is what? According to this, 0. Now think about this. You have a numerator that's headed to a non-zero number. Limit x goes to 5 of, let's say, x over. So here the top is going to 5, right? Let's say that I could make the bottom, this bottom, I could make it approach infinity. Then what's happening is that you have a number on top that's kind of staying where it is and the bottom just grows. And we know that when you have a fraction, if the numerator stays the same, the denominator gets big, the ratio gets smaller, and it goes to 0. Yeah? You okay with your number sense on there?
It approaches 0.
It approaches 0. Does it ever get there? Not necessarily. But the limit, remember, doesn't ever tell us what's happening when we get there. It's what we're approaching as we go. All right, and then the bottom left is 4 different things. And I'm not going to get into each of the 4. I just want to put it up here. If you have fixed over 0. Now we could have positive and positive, positive and negative, negative and positive, negative and negative, all these different scenarios. I just want us to think about what would be happening here. Let's say again we have a number that's fixed on top, like let's say the number 5. And the bottom starts getting smaller and approaching 0. What happens to a fraction when the numerator kind of stays the same, but the denominator starts to get small? The ratio should get bigger. It's the opposite of this, right? Numerator stays the same, denominator gets big, ratio gets small. Here, if the numerator stays the same, denominator gets small, fraction gets big. So they're like inversely related. Make sense? So this should do something like get big. And you can see there in the table there's different possibilities, right? Infinity, negative infinity. So we are going to study today the one I circled in red earlier, infinity over infinity. We are going to do this one, and we are going to do this one. Those are the 3 things, the 3 topics for today. All right? Wow, and I only have an hour to do it now. So the first topic is called infinite limits. And there are two major topics today. Infinite limits, and the next topic after this is called limits at infinity. Totally different. Infinite limits involve this. We're going to take a limit, and let me get my little, I pulled some problems out of another book just to go off of today, maybe. Okay. Forget it. Okay, infinite limits. Let's say we're taking the limit as this goes to this. Do you remember when I did that with the sine? I said like it didn't matter what was going on there. Junk, and then we had junk over junk, all that. Okay, this is just telling you, hey, look, you're taking a limit. Who cares what it's doing? And you're doing some function. And then when you do it, you get this form. You get the form of a fixed number over 0. These are called infinite limits. Anytime this happens. It's not 0 over 0. It's a non-zero number over 0. There are going to be there are three different things that could happen. This will go to one of the following three things. Sorry, that red is no good. It's either going to be infinity is our answer, or we might get negative infinity as an answer, or the last possibility is that the limit just will not exist. And that's it. Those are the only three outcomes that are possible if you ever see a limit like this. All right? And the reason is, like we said earlier, if a number's staying solid on top, staying where it is, and the bottom gets small, that ratio must get big. The question is only, is it getting big positive, or is it getting big negative, or possibly, where do you think the does not exist would come from? Where did does not exist come from earlier, when our limit was what? Not approaching the same from the left and the right. So this scenario is going to happen when we're coming in from two different sides and getting two different infinities. Infinity on the left, maybe, and negative infinity on the right. I think you just need to see an example so you can see how this all works, all right? Big picture though, infinite limits involve this form, and we have three outcomes possible. That's it. Do you see me saying you need to do algebra or trig or conjugate or anything? You don't see me saying that, right? Because you don't need it. So let's do our first example. And we'll take baby steps. Limit x approaches 5 from the right of x plus 1 over 5 minus x. I could graph that, right? I could graph this function, and you could get an idea of what it's doing. And you could tell me what the graph does as you approach from the left, from the right, sorry. You could, right? We're going to try and do it without a graph. So let's just look at the form we have. Where's the numerator headed? 5 plus 1, it's headed to something really close to 6, right? Really close to 6. And that is definitely without any hesitation, that's a positive number. I'm putting a plus there to mean that it's a positive number for us. All right? It's positive.
Is it really important to make sure that we put this?
That'll help us with our answer at the end, because we do have to take into account that it's positive. Yeah, just put it there for now. Now, what about the bottom? Where is it headed? It's headed to 0, right? It's headed to 0. So we have fixed over 0, right? And so we know there's only three outcomes. It's positive infinity, negative infinity, or it doesn't exist. Now this is a one-sided limit, so we only have to approach 5 from the right. We don't have to look at both directions. So what I'm going to do is I'm going to just analyze this ratio a little bit more using this information. And to do it, I think I'll just draw a number line. I'll put the number 5 here. I'm just going to put some arrows coming in like I'm coming in from the right. And I'm just going to do kind of like a little test point. Like what would happen if I picked a point that was a little bigger than 5? Like let's say 5.01. And we could argue, you know, is that close? Well, I could do 5.001, but I think that's good enough for us to be able to say we're to the right of 5. And let's just see the behavior we have. If I were to take that and plug that in to the top, right? If I plug that in top, I'd still be close to 6, right? Really close to 6. So the top, I'm using this to determine that the top is still going to be close to 6, which of course is a positive number. The bottom we know is approaching 0. We know that. But is it going to be a very, very small positive number or a very, very small negative number?
Very small negative.
Small negative number. How do we get that? Well, just take this number right here and plug it right in there for x. What's 5 take away 5.01? Negative 0.01, right? So this bottom piece right here is headed to negative 0.01. And if I took an even smaller number, or even closer, 5.001, then when I put it in here and subtract it, I would have negative 0.001, wouldn't I? And then even closer, I'd have another one. But no matter what, they're always negative on the bottom, aren't they? So you have a positive number that's fixed, or not really moving, right? Divided by a number that's getting smaller and smaller and smaller, but is always negative. So I come back up here and I say, I know a little more about this 0 now. I know that that's always a little negative. I always know that that's a little negative number, right? And what were my 3 possible answers? Infinity, negative infinity, or does not exist. Well, a positive number divided by a negative number would have to be negative. So this is only going to be negative infinity. And we're done. So I just put my answer, you know, I would just write the limit down again. And you might be sitting there saying like, well, how do I show my work for this, right? Like, how do I show my work? You need to just show me that you know that you're getting this form. You need to show me a little bit of analysis that you've actually considered which side you're coming in from, and that you've analyzed what happens when you do. And from that, you should be able to determine the answer. That's all I need to see. There's no like formal process that has to be done. What I don't want is you just typing it in a graphing calculator and just looking at where it goes and putting in your answer. I need something. All right? You can use that as a check. That's fine. Any questions on this?
What do you have a 33% chance of getting your answer right?
You do. I told one of my students in my other class asked me, can I just like guess? Like, what if I just guess and get it right? Like, will I get credit? And I told him, I said, I'll make you a deal. If you bring in a 3-sided coin, I'll let you use it on the test and give you full credit. So I'll let him produce a 3-sided coin.
That would be very difficult.
I hope so. All right, so same problem, other side. Let's come in from the left side. Is that going to change things?
Yeah.
Probably, right? Everything's going to set up the same. We're still going to be headed to 6 over 0. I know that the top is going to be positive. Right? As long as I'm close to 5, right? As long as I'm close to 5, adding 1 to it is still a positive number. Right? Still. So positive on top. I have fixed over 0. I've got a problem. I've got to go solve this, but I know there's only 3 answers. So I draw a number line. Here's 5. I approach 5 from the left this time. So give me a number over here. 4.99. And now if you take that 4.99 and you plug it into the numerator, you'll get a number that's still really close to 6, right? 6. It's actually 5.99, but it's still positive. That's all I care about. And the denominator, though, this is a little different than last time. It's 5 take away 4.99, which leaves you with 0.01? 0.01. Right? And that's positive. And if I got even closer, 0.4999, this would be 0.001. And so no matter what, as I approach 5 from the left, the bottom is going to maintain the fact that it's what? What am I concerned about? That this thing is what? Positive, right? And that's a positive over a positive, which is positive. So the answer is positive infinity. Done. Now, in my other class, I had some students ask me like, okay, so is it always going to be that? If I come in from the left, the answer is positive infinity. If I come in from the right, it's always negative infinity. No. You have to check it. All right? What if I did this limit, started the problem over, and I didn't put that? You have to check both sides, wouldn't you? Just like you did before. And what would you get if you came in from the left, which we just did? You would get positive infinity. And if you come in from the right, you would get negative infinity. So what would that mean? Doesn't exist. Right? It wouldn't exist. Because positive and negative infinity, although they are both very large, one is positive, one's negative. So DNE would be the answer here. All right? Any questions? Fixed over 0, you analyze it, you pick some test points, you kind of go, what's happening on the top and bottom, and then you make a conclusion. We should try another one. How about this? Let's go to a different number. How about we go to, let's go to -3. And let's do x minus 3 over x plus 3 squared. Please take note that I did not tell you which side to come in on, which means you got to check them both, right? But let's first try and determine what this is doing behavior-wise. So, -6 on top, right? It's headed to -6, which of course is a negative number. I'm just going to kind of mark it up here so we know that's a negative number. And the bottom is headed to 0, right? -3 plus 3 is 0. So I know the bottom is going to 0. I have fixed over 0. So I know it's either infinity, negative infinity, or does not exist. And I just need to figure that out now. So let's first analyze this one. What's the limit? Let's come in from the left first. X approaches -3 from the left of x minus 3 over x plus 3 squared. So I would now go and I would pick a point, right, to the left of -3. And I recommend drawing a number line. What's that? -2.999. So I give this problem intentionally because a lot of students forget this. And it's like, oh yeah, look at your number line. If you're on the left side here, right? -4 is on this side, -2 is on this side. So a number to the left is actually -3.1, 3.01. The tendency is to say -2.99, all right? I know that you weren't the only one here who thought that, for sure. So I would take a number in here like -3.01, and that's what I'm going to use in there. What about the top? If I take this number and I push it into the top, I get something that's really close to what? -6 over, now I know the bottom's going to 0. I know this should be a small number, but let's try it. What would happen if I put -3.01 right there plus 3? I get -0.01, right? But it's squared. Don't forget that, right? It's squared. That's critical. Because really now, it does not matter that it was negative, does it? It's going to be positive. Do y'all see that? Because of the squared. And that means that the bottom is going to maintain being positive no matter what. But the top is what? Negative. So what's a negative divided by a positive? Negative. So this should give you negative infinity. I should put it on this one right here. This one is negative infinity. This was the left limit. The left limit gave us negative infinity. Does anyone see what's going to happen when we come in the right side? Yep. It's not going to matter, right? Because again, no matter what I get there, I know it's going to 0, but I'm squaring it. So it's going to be positive again. And the top is going to be negative 6 still, and we're going to get the same answer. The answer is going to be negative infinity for this limit. Now I'll write it down just so we have it. Limit x goes to negative 3 from the right of x minus 3 over x plus 3 squared. And I know that that's going to be a number from the right side. So here's your negative 2.99. You plug that in. I know the top's going to negative 6. The bottom is going to, this time, 0.001 squared. When I plug in negative 2.99 here, I get that. And squared, who cares? It's positive now, so same thing. Negative infinity. Any questions? No?
So it usually happens, like when you have a square at the bottom, it's usually going to end up being...
Yeah, when you see the square down there, or fourth power, something like that, you pretty much know that you're going to have the same thing happen from both directions.
I guess where it gets funny is where you have the odd.
Yeah, okay, so what if it was odd? What if this was cubed? What if it was cubed?
It would not exist.
It would not exist. So this would be cubed, and when we plug this in, it would be negative cubed. It would stay negative, right? So from one side, we would have negative over negative, which would be positive infinity. And then if we came in on this side, if this was cubed, we would cube a positive, it would be positive. Negative over positive would be negative. So now we would have the opposite happening. So basically, if you see squared, fourth power, sixth power, you can pretty much be guaranteed it's going to do the same thing from both sides. If it's odd, it's probably going to do opposite. So DNE.
All we have to figure out is which way it's going, negative or positive.
Yeah. But you still have to pay attention to what's happening in here. Because if I flip the 3 plus x over or something, it could change what's happening. So analyze it a little bit. All right. Let's do another one. I think this might be my second to last one that I'll do. You've got to go in here and get your hands dirty, right? There was one. Here we go. Limit x approaches, where the heck is it? Oh, I'm on the wrong page. That's why I'm like, where is that problem that I was going to give you? Here we go. X approaches 2 from the left of x cubed minus 5x squared plus 6x over x to the fourth minus 4x squared. So if you want to know what's happening with this limit, you have to plug 2 in, don't you? Let me just make sure it was 2. Not, oh, wait, it's negative 2. Yeah, this is negative 2. My apologies. We would have to plug in negative 2 to see what's happening. Which you could do, right? Let me just try it out here. Let's see. Negative 2 cubed, right? Negative 8. Negative 2 squared is 4 times negative 5 would be negative 20. And then negative 2 times 6 is negative 12. So the top is not going to 0. Agreed? The top is not going to 0. It is going to negative 40. All right. And the bottom is negative 2 to the 4th power, which is 16 minus 4 times, minus 16, and there you got 0. So you've got a situation here where you have fixed over 0. And when we see that, we're thinking 3 answers. Just got to figure out which one it is. Now, I could do a number line right now. I could, and I could start plugging that test point in and figure out what happens. Yeah, but it might be easier if we see that we can do some factoring first. Let's just work on it algebraically. This is just to see if we can clean it up. The top is x, and then x. Do you want me to factor it all right now? Okay, so this would be minus 3x minus 2. If I factor the numerator out completely, and the denominator, I could factor out an x squared, and then what would be left would be an x squared minus 4, which is a difference of squares, so that's x plus 2, x minus 2. That's what would happen if I completely factor. Can we cancel any of these factors? You can cancel one of these x's out, right? You can say, all right, that's gone, and make that, what, a first power instead? Anything else? X minus 2. You can cancel x minus 2 so long as you promise me that x is not what? 2. Well, I'm not even close to 2, right? I'm going towards negative 2, so I'm not even near where this would potentially have a problem, so I can cancel that factor. And all you're left with is x minus 3 over x times x plus 2. Keep in mind, I only did this to just clean it up a little bit. I did not have to do this. It's a little easier to plug in right now and figure out what's happening with the signs. So are you ready to come into negative 2 from the left now? Here's a little negative 2. We're coming in from the left, which is this side. Number over here, negative 2.01. Good enough. That'll work. Plug it into the top. About negative 5, yeah? Negative 5-ish. That's a negative number, right? Okay. On the bottom, now be careful. We've got a little more going on here than just this piece. We've got this out here, right? What happens if I replace this with negative 2? Negative 2, right? Really? Oh, well, sorry, negative 2.01. It's negative. It's close to negative 2, right? Negative 2. I could put 0.01. I don't have to. What are we concerned with? I mean, what's the only thing we're looking for here?
You don't want to get 0.
The signs, right? We just want to know the signs. They're positive or negative. Positive. That's all we want. We know negative 2, bottom left. That's going to be a negative number. Times this thing, I know that's going to 0. This is what caused the whole problem to begin with, right? The question is it going to 0 through negative numbers or positive numbers? So plug that in right there. That's going to be a very small negative number, right? So I'm going to put negative 0.01. If you have 2 negatives on the bottom, they're going to multiply to be positive. Negative on top. Negative over positive? Negative. So the answer is negative infinity. We're done. Because it was only one side we were coming in from, right? That was the second to last example for that topic. Here's the last one. Y'all need to let me know. Is this making sense? Everything's registering okay? All right. Let's try this. Limit as x approaches 0. Let's come in from the left side of cosine of 4x minus 1 over sine of 5x. plus 1 up there. Sorry. Plus 1. So when we were doing this last class, was it last class? The trig ones? Maybe it was the one before that. Last class was continuity.
We had a couple.
Yeah, but I think we started class with some examples of this trig stuff. What we were trying to get was sine junk over junk, right? That's what we were trying to get. But remember that when we did that, it's because we had started at 0 over 0. That's when we did the form, we were getting 0 over 0. Check this one. X goes to 0. 4 times 0 is 0. Cosine of 0 is 1. 1 plus 1 is 2. The top's headed to 2, not 0. The bottom is headed to 0. So I already know now it's one of 3 answers. What you want to be careful with is on the test, seeing this and start thinking, oh, I need sine junk junk. Right? You don't need sine junk junk here because you don't have 0 over 0. This is one where you're going to figure out whether it's positive or negative to determine one of those 3 answers, right?
Would you instruct the difference on a test?
Would I what?
Would you instruct the difference?
I would not tell you that there's a difference between the two. You would have to recognize it. Because the first step to doing any limit is checking what the form is. If you get 0 over 0, you're doing some algebra. If you've got trig stuff in there, you're doing some sine junk over junk stuff. If you're getting fixed over 0, you're analyzing the function by taking a test of what's happening from that side. So you've got to be able to distinguish between those methods. All right, you ready to talk about this? Yeah? Okay, I'm approaching 0 from the left, so I'm coming in this way. So I could take a little small negative number like negative 0.01, right? And then I could start plugging it in and figuring out what happens. Which means I probably need to get my calculator out, right? And I need to plug it in. I'm going to do it without a calculator though. What do we know for sure the top is headed towards? 2, right? We already know that. That's not an issue. It's headed to 2. So I know the top's headed to 2. The only real question is to figure out what the sign of the denominator is, if it's positive or negative. Well, here's your denominator. And in pre-cal, you at some point, I'm sure, were asked to graph that, or to understand how to graph it. And I hope we would all know what a sine curve looks like. 2 pi is the period, right? And it goes like this. Right? There's your sine curve. And it extends in both directions, so it goes back that way, and it goes actually in both directions forever. So if I put a 5 in front of the x, what effect does that have on the graph? What does it do?
Compress. Makes it taller.
Taller?
Compresses it.
Compresses it. Okay, so remember, if you change the number in front of the sign, that changes your amplitude. If you change the number in front of the x, it affects your period. All right, so there was a formula that if you had something like this, a sine of bx plus c, like that was a general form of a trig sine function, that a was your amplitude, change a and it changes this. If you make that negative, it flips the whole thing over. The b, if you take 2 pi and divide it by b, that's your new period. So when this is a 1, 2 pi divided by 1 is 2 pi. But if b was 2, you would do 2 pi divided by 2, which would be pi, so that would cut it in half. If you do 5 here, this would be 2 pi divided by 5, which would be 2 pi over 5. That's how long the period is. So putting a 5 there actually compresses it. You're going to get more waves in a shorter amount of time. The C was what we called a phase shift. That moved things like left and right. Okay. What's important for us to know is that we've got signs happening. It does not change this point. It does change this point, but you're getting more of these happening faster.